IB Chemistry 12 SL workshop. I'm Peter, and I will take you through the highlights as we cover topics 6 to 10 in this particular workshop from the Oxford textbook. And topic 6 is chemical kinetics, where the key topics are collision theory and rates of reaction, catalysts, both homogeneous and heterogeneous, the Maxwell-Boltzmann energy distribution and how it changes as a function of temperature, and of course the various factors that affect the rate of a chemical reaction, namely temperature, catalysts, concentrations of various reactants, and the particle size of reactants if solids are involved. Okay, so let's start with a couple of simple sample problems to get us oriented in terms of what we're looking for. So here we have the rate of a reaction between two gases increases when the temperature is increased and a catalyst is added. And the question asks which statements are both correct for the effect of these changes on the reaction. So if you increase the temperature, you have the options A, B, C, and D. And if you add a catalyst, you have the options A, B, C, and D. Which of the statements is correct for both? And C indeed is the correct answer. Very good. Because increasing the temperature doesn't change the activation barrier, it just increases the number of molecules that have sufficient energy upon collision to surmount the barrier and the reaction to occur. Adding a catalyst, on the other hand, of course, provides a new reaction pathway with a lower activation energy. Very good. Good positive start. Let's move on. In general, the rate of reaction can be increased by all of the following, except B is indeed the correct answer, because all the others do increase the rate of the reaction. All right, let's move on. I think we have now the first short answer question, in which I'll show you a graph of the volume of carbon dioxide produced when excess, and note the fact that it's excess calcium carbonate, is added to a certain amount of 2 molar hydrochloric acid. As you notice, it sort of starts off and then levels off until finally it basically plateaus. So the first request is to write a balanced equation for this reaction. And this frequently comes up, so that's why I put this on here. The reaction in this case now is calcium carbonate. I will write it down here. CaCO3. Maybe I shouldn't have it quite that thick. We'll make it 2 point. That's better. CaCO3 is a solid reacting with 2H plus, which is the acid, aqueous, goes to form calcium 2 plus aqueous, plus H2O as a liquid, plus CO2 as a gas. So initially, basically, you form carbonic acid, H2CO3, which is nothing more than carbon dioxide dissolved in water. And you're monitoring the loss of the carbon dioxide from the reaction. But the key point here is the hydrochloric acid is rate limiting because you've got the calcium carbonate present in excess. There shouldn't be a 3 there. That's an error on my part. Get rid of that 3. There we go. Okay. So the next question then says, explain the change in the rate of the reaction with time. Well, what you need to notice, of course, is that the rate of the reaction starts off fairly steep, and then starts leveling off less and less and less, until finally it plateaus and basically the reaction has stopped, by which point all the hydrochloric acid has been consumed. How would you determine the rate of the reaction at any particular time? You would take a tangent at any point on the curve. So for example, if you wanted to find out what's the rate at this particular point in time, you would then do a tangent to the curve and pick a couple of points and calculate the slope. And that would be the rate of the reaction volume of CO2 per unit time at this particular time down here. Okay, because there's different ways that you can measure the rate of a reaction. You can do the initial rate, which would be the tangent right here at the beginning when it's the rate is the fastest, or further along, or you can do an average rate between 2 points. All right. Let's then move on. Whoops, I got the wrong thing. We move up. Okay, so on the above graph, they want you to draw the curves you would expect if you had the same volume, but now 1 molar instead of 2 molar, or you double the volume and it's 1 molar still of HCl. So to simplify the task, I will just recreate the original plot here, and then we can take a look at how the plot changes as a function of time. So this is the volume of CO2 versus time. And the original plot started off here, and it went up and it leveled off, something like that. Okay, so now I'm going to do the second one, the same volume, but now 1 molar HCl instead of 2 molar, and I'll do that in yellow or orange. And the thing to notice is now, since it's less concentrated, the initial rate will be slower than we started with. And of course, we only have half the quantity of HCl in terms of the moles. And so the reaction, therefore, will plateau at a different level. So a typical plot here would be something like this. And it will plateau at exactly half the value of the blue curve, which is the original one. Then the other variant, we take the same 1 molar, but we now take twice as much of it. So we now have just as much HCl as we had originally, but it's at half the concentration. So that means it'll start off slower. So I'll do this in red. This will start off slower along here, and then ultimately we'll end up at the same point because, of course, we have the same amount of acid. And so those would be the 3 curves that you would see. The orange one is I. This is I. The red one is II. I should make that a 3 instead. Oh, it is 3.5 point. I'll make it 3. Make it simpler. Right. So the key point is the initial rate is determined by the concentration of the acid. Where the plot ends up is determined by the amount of acid that is being used in the reaction, because it's the limiting reagent. And again, if you have any questions, don't hesitate to ask, okay? All right. So here, the question now asks to draw a graph that shows the distribution of energies in a sample of gas at 2 different temperatures, T1 and T2, such that T2 is greater than T1. So basically, we're talking about Maxwell-Boltzmann plots here. So here's my axis. And then now here, the axis is labeled, the y-axis is number of particles. And the x-axis here is energy. Okay, so we'll do two different plots. I'll do one in blue at temperature T1, which will look something like this. It'll go up and then come down like so. That's not bad. This is T1. And then we'll do T2 in green, and we'll make it 3-point again so that we're not swamping it out like so. And that plot, again, will have the same area underneath the curve as the blue one, but it will now be shifted so that it'll look something like this. There, so this would be T2. So the average energy has now moved up because you're at a higher temperature, because T2 is greater than T1. But again, the area under both curves is the same. All right. Oh, they ask you to define the term activation energy.
Hi, Peter.
Sorry, yes.
Peter, we have a question. It seems one of students is asking for, can you explain a little bit more about Maxwell-Boltzmann? What does it represent? How does it work and stuff?
Oh, okay. Thank you. I can do that.
Thank you.
So let's take a look back at what we have here. The Maxwell-Boltzmann is essentially a distribution of the energies amongst the various gaseous particles. Right, so I've got this graph in a sample of gas. And remember that according to collision theory, in order for reactions to occur, the molecules have to collide. They have to collide with sufficient energy to clear the activation barrier in order to react. And they must have the correct orientation to produce the desired products. And so the area under the graph is the total number of particles in this particular gaseous sample. And the two curves here simply show you what happens to the energy distribution as you increase the temperature. So if you, for example, decrease the temperature, I could do that in black, you would then have the situation, the curve would be something down here, and then coming down like so. Because the energy now would be less, right? But T1 and T2 show basically as you increase the temperature, the curve flattens out and there's more molecules having higher energy than at T1. Okay? All right. So then the question is asked, what do we mean by the term activation energy? And my favorite answer to this one is to simply indicate it's the minimum energy required for a reaction to occur. Whoops, why am I writing in black? Well, we'll go in black. The minimum energy required for reaction to occur. So in the Maxwell-Boltzmann plots, you could then indicate that if the activation barrier was, let's say, here, whoops, that's supposed to be a straight line, that's my shaky hand, then the molecules that are under the curve, for example, at T1, this number of molecules will be able to undergo the reaction. For T2, it's going to be a larger area simply because you have more molecules under there. So for T2, all of these molecules would then have sufficient energy to react, right? Because they've managed to surmount the activation barrier. Remember, the reaction profile looks something like this. It goes up and down and so on. This is for an exothermic reaction where you're plotting energy, potential energy versus a reaction coordinate. And the activation barrier is this beast right here. That's EA. Okay? All right. So the effect of a catalyst on the rate of an endothermic reaction. Basically, the catalyst speeds up the reaction. It speeds the reaction. Remember, the catalyst doesn't alter where you start and where you finish. It just simply provides a different path between your starting point and your end point. And of course, it speeds up the reaction because it lowers the activation barrier. And so as a result, more molecules are able to surmount the barrier. Hence, they clear the minimum energy required for the reaction to occur. You should have a C in here. Nobody picked up my misspelling. Reaction to occur. Okay. And that's basically the key points that you need to know about the chemical kinetics. All right, to remind you again, the key points. Collision theory and rates of reaction. Remember, there's three things required in collision theory. What catalysts do, the Maxwell-Boltzmann energy distribution, we just saw that, and the factors that affect the rate of a chemical reaction. Okay, all right. I think we're ready to move on to topic number 2 or topic 7 in the textbook, and that's equilibrium. Now, what you need to know in this chapter is you have to understand the equilibrium law, which is that equilibrium is a dynamic process. It's not that things are just sitting there doing nothing. It's that the forward and reverse reactions are both proceeding at the same rate. So the system looks like it's stagnant when in fact it's dynamic. You have to be able to write equilibrium constant expressions for any particular equilibrium. You should be able to combine equilibrium constants. By that I mean, if you do a reciprocal reaction, what happens to that? If you combine two constants and so forth. I'm not going to dwell on that today. And then the key thing that they often ask is Le Chatelier's principle. When they ask you to say, okay, how will the equilibrium change if you change concentration, change pressure, change temperature, or you put in a catalyst? And we'll look at all of those today. All right, so here's our first sample problem. We have this reaction involving sulfur dioxide and chlorine in a closed container to form thionyl chloride, which has a delta H naught of minus 85 kilojoules as written. So the question then is, which of these statements is correct? Will decreasing the temperature increase the amount of product? Will increasing the volume of the container increase the amount? Increasing the temperature, etc. And we have B, increasing the volume will increase the amount of SO2Cl2. Unfortunately, that is incorrect, because if you increase the volume, that means you're lowering the pressure. And if you're lowering the pressure, the equilibrium will shift to the side that will increase pressure. So in this particular equilibrium, you have two gaseous particles on the left, one on the right. If you diminish the pressure, the equilibrium will shift to the left to make more SO2 and Cl2, because basically you're trying to counteract the change that's been imposed upon the equilibrium. So unfortunately, B goes in exactly the opposite direction. If you increase the volume and lower the pressure, the equilibrium shifts to the left. The correct answer is A, decreasing the temperature will increase the amount of SO2Cl2. And that's because this reaction is exothermic. Remember the sign convention? If delta H is negative, that means heat is lost from the system to the surroundings. Or you can think of it in terms of heat is a product of this reaction. So if you remove some of the product, the system will shift over to produce more of said product. And in this particular case, that means it'll switch over to making more SO2Cl2. Okay? All right, we're going to see a bit more of these variants a little bit later on. All right, here we have a situation with an equilibrium between bromine and chlorine to form bromochloride, which is a delta H of plus 14. Which is the correct answer here? D is indeed the correct answer. Well done. Because since delta H is plus, that means the reaction is endothermic. So heat is a reactant. Consequently, when you put heat in, the reaction will shift to the right. It will produce more product. So the volume of the equilibrium constant will increase. Remember that the equilibrium constant only changes when temperature changes. Otherwise, it remains constant throughout. Very good. All right. Here we have the Haber process. A very famous reaction. Nitrogen reacting with hydrogen to form ammonia. Essentially functionalizing nitrogen, dinitrogen, which is a fairly inert molecule. And this is a key step in producing fertilizers. So the first question they ask is to state the equilibrium constant expression for this reaction. And again, as I say, you have to be able to do this for any reaction that you are given. So in this particular case, let me go back to blue. The equilibrium constant K will then be equal to the concentration of NH3 squared divided by concentration of N2 times the concentration of H2 cubed. And as I say, that is a constant if temperature is kept a constant. If, on the other hand, temperature changes and the equilibrium shifts, then K will change. All right, so then it says predict, giving a reason, what will happen to the position of equilibrium if the pressure in the reaction vessel is increased. So if the pressure is increased, therefore the equilibrium wants to adjust in the opposite direction. Namely, it wants to diminish the pressure. So therefore, since you've got 4 gaseous molecules on the left-hand side, only 2 on the right, therefore, the equilibrium will shift to the right. And so the making of the ammonia will be favored by low pressure. All right, that's the way you always do this. You count the number of gaseous molecules on both sides. And if the pressure is increased, then to diminish that, to counteract the change, you therefore equilibrium will shift to the right. To the right. Because you have 4 particles as reactants, but you only have 2 gas particles as products. So in other words, if you're trying to do this particular reaction to get as much yield of the product as you want, it's advisable to run it at lower pressure. All right. What's the effect on the value of Kc when the temperature is increased? Kc is this beast that I wrote originally because, of course, I'm indicating the concentrations of the various species in moles per liter. All right, temperature is increased. So delta H is negative, which means it's exothermic. Heat is the product. So if I increase the temperature and put heat in, that's going to be pushing it back to the reactants, N2 and H2. And so therefore, advisable, if I'm trying to do this reaction productively, I want to run this at a lower temperature. And so therefore, in answer to the effect on the value of Kc, Kc decreases because I'm making more reactants. Kc decreases. And equilibrium shifts to the left. So therefore, ideally, to run this reaction to give you the best yields, you therefore would do this in a situation where you would increase the pressure and you would diminish the temperature, right? Because those are the 2 features that would then favor this reaction producing more ammonia when it reaches equilibrium. Explain why a catalyst has no effect on the position of equilibrium. That goes back to the fact that in equilibrium, shown here, the rate of the forward reaction equals the reverse reaction when the system is at equilibrium. All the catalyst does, it speeds up both the forward and the reverse reactions, but it doesn't alter the position of equilibrium. You just basically get to the equilibrium situation faster. So the answer to be put in here is that the catalyst speeds up both the forward and the reverse reaction. Speeds up. Both forward and reverse reactions. And it does so, I think the key word here is equally. And we'll underline that. So it's still at equilibrium, but it's getting from forward and reverse at the faster rate. So as I said, the catalyst helps you attain equilibrium. It'll be the same equilibrium, but it will get you there more rapidly. Okay. Here we have a reaction between colorless bromide ions, that's Br minus, with colorless hydrogen peroxide, which is H2O2, to form a red-brown bromine solution. That's the Br2 aqueous. And you notice that delta H for this is negative. So again, this is an exothermic reaction. So the question asks you to predict and explain the effect on the position of equilibrium when you add a small amount of sodium bromide solution. Well, if you're adding a small amount of sodium bromide solution, you're putting in more reactant. You're adding Br minus. So if you add more reactant, the system has to shift to the right in order to attain equilibrium. Right? Because basically, this is a good time to mention this. You can always write a reaction quotient, Q, which you may have seen in your classes, which looks like the equilibrium constant, and you can plug in the numbers. And in the particular case we have here, you can then see whether Q is less than K, is Q greater than K, or in fact, if Q is equal to K. Q is the reaction quotient. So if it's less than the value of the equilibrium constant, that means the reaction has to shift to the right because your numerator is too small. If on the other hand, Q is greater than the equilibrium constant, that means your numerator is too high. You have to increase the denominator, so it'll shift to the left. And if you have a situation when Q is exactly equal to K, then the system indeed is at equilibrium already, and nothing has to change. So that's one way to assess where you are relative to the equilibrium position. But here now we have the situation we've deliberately added extra reagent, and so we now have the position of equilibrium will shift to the right. So it's favoring the forward reaction, so it's making products. Okay, and that same would be true if I added a little bit of H2O2 aqueous as well, or H plus, either one. If I add reagents, reactants, then I will be favoring formation of more products, and the position of equilibrium will shift to the right. All right, the second situation, we add a small amount of sodium hydroxide solution. And your first reaction is to look at this and say, but there's no sodium hydroxide here. So I took this off an old exam because this relies upon you remembering acid and base chemistry. Namely, that if you add sodium hydroxide, you will then consume some of the H plus, because of course the standard reaction that you all know and love is H plus plus OH minus goes to H2O. Actually, this should be written as H3O plus, but we're taking the shorthand route. So in other words, adding a small amount of sodium hydroxide means we're diminishing the amount of H plus in solution. In other words, we're removing a reactant. And so now in this case, the equilibrium will shift to the left. Namely, we saw in part A, if you add a reactant, it shifts to the right. In part II here, if you remove a reactant, the equilibrium will shift to the left. And so basically, this reaction is producing more water, which again makes it shift to the left. And finally, and they like to ask this question a lot, what happens if you add a catalyst to this reaction? And the answer in big letters, no effect. Adding a catalyst does not shift the position of equilibrium because, as I said earlier, it increases the rate of both the forward and the reverse reactions equally, and the equilibrium constant remains the same. Or if you want to think of it, it lowers the activation barrier for both the forward and the reverse reactions equally. Okay. Then what happens to the value of the equilibrium constant when the temperature of the reaction is increased? All right, so now this is a situation in which it's an exothermic reaction. So again, heat is a product, so we're pushing it to the left, which means that the denominator of the K expression will increase in magnitude, the numerator will diminish. And so the answer that I would write here is that you have K, effective equilibrium constant, K decreases. Or Kc, I guess I should call it, K decreases. Because again, it shifts to the left. Remember, temperature is the only thing that will change the magnitude of K. And that's the situation here, because since the forward reaction is exothermic, the reverse reaction is endothermic, and that will absorb the heat, and that's why it shifts to the left. And finally, we want to state and explain the color change when hydrochloric acid is added to the reaction solution at equilibrium. So if we add hydrochloric acid, we're adding some of this reagent, H+. So again, we expect it to shift to the right, which means we're now producing more bromine. And so the expectation is that the addition of acid will end up forming more bromine, which will increase the red-brown color. And so the answer you could put down here, it goes to a darker red-brown. And that's because you produced more bromine. So those are the typical sorts of questions that you see asked about systems at equilibrium, particularly applying Le Chatelier's principle. When you perturb an equilibrium, what happens? Right? The equilibrium law is dynamic. You know how to write the K for whatever equilibrium it is, but you should practice looking at what happens to equilibrium when you change concentrations of reactants or products, pressure or related volume, if it's a gaseous system. Temperature depends upon whether it's exothermic or endothermic. And of course, the effect of a catalyst is 0. And I showed you how you can use a reaction quotient to get an idea whether you are at equilibrium or whether you have to shift right or left to attain equilibrium. I see my boss looking at me saying,
there is a
we have
question.
a question.
Yeah, I don't know if it's directly related or not, but anyways, it says that are reactions at equilibrium. Are all reactions at equilibrium.
Are all reactions at
Just
equilibrium?
every reaction that we
They are
have.
not.
They are
No,
not.
no, no, no. Some reactions go completely to completion. These are systems in which, well, what the best example I can give you is, it's going to come up a little bit later when we talk about acids and bases. A strong acid undergoes complete reaction with water. A weak acid sets up an equilibrium. It does not go to completion. So you always have to be careful. But here we're talking about reactions that don't go to completion. So in other words, when you combine, in this case, nitrogen and hydrogen to form ammonia, in the final mixture, you will have all three gaseous species present. If this was an irreversible reaction and it went all the way to product, then the final mixture would only contain ammonia. It would not contain dinitrogen or dihydrogen. Okay. Does that answer the question? I'm looking for a hint. Okay, I'm assuming, oh, speaking of acids and bases, that's our very next topic. There's a lot of stuff in acids and bases, I got to tell you. Arrhenius' theory, you may recall, was that acids are species that contain H+, bases are species that contain OH-. That was then supplanted by the Bronsted-Lowry definitions of acids and bases. Acids are those species that provide H+, bases are those species that acquire H+. And amphiprotic species are ones that can do both. But whereas you see in the Arrhenius theory, an acid plus a base would give you a salt plus water, in the Bronsted-Lowry definition, a reaction of an acid with a base gives you another acid and another base, which are the conjugates of your starting reactants. Then you have to know the properties of acids and bases. You have to know how they react with metals, bases, and carbonates. Acid-base titrations are basically from your stoichiometry from topic number 1. So I'm not going to go through that today. There's the pH scale. The thing to watch out on the pH scale is the natural tendency to think that as pH goes up, therefore the concentration of the H3O plus ion must go up. Not so. The bigger the pH, the weaker the acid. Because remember, it's the negative log of the hydrogen ion concentration. Then we can talk about strong and weak acids and bases, and we'll do that. And then how you can determine whether an acid and a base is strong or weak. Okay, so to get you thinking about acids and bases, here's a fairly straightforward multiple choice question. If you take 1 molar solutions of these various species, how would you rank them in terms of pH, lowest first? Unfortunately, D is not the correct answer, because you're therefore saying, when you got the first 2 right, nitric acid is a stronger acid than carbonic acid, but ammonia is a weaker base than barium hydroxide. And so in fact, the correct answer is A, where you start with strong acid, you go to weak acid, weak base, strong base. So D has these 2 interconverted, and that's what makes it incorrect. And of course, the ones here in the middle, they got the basis first, and that's no way that can be. Yeah, and we'll talk about what makes acids strong and weak in just a moment. All right. Here we have another multiple choice question to distinguish between strong and weak monoprotic acids. Uh-oh, maybe we better go over each of these in turn. If you add magnesium to each solution and you measure the rate of the formation of gas bubbles, that indeed will differentiate, because the strong monoprotic acid will evolve gas bubbles faster than the weak acid. If you add aqueous sodium hydroxide and you measure the temperature change, the strong acid will be more exothermic than the weak acid. And so you will see the temperature change. You can differentiate. If you use each solution in a circuit with a battery, you will see that, in fact, for the strong acid, the lamp will grow brighter because it's a better conductor. Right? The strong acid is completely dissociated. The weak monoprotic acid, the light will not glow as much. And so again, you can differentiate between solutions of strong and weak monoprotic acids. So the correct answer here is D. All three of these can be used in order to differentiate. And again, that simply reflects the fact that the strong acid generates, if I talk about 1 molar strong acid like hydrochloric acid, I know that I have 1 molar H3O plus in solution. If, on the other hand, I take a weak monoprotic acid like ethanoic or acetic acid, then my concentration of H3O plus is much less than 1 molar. And that will be manifested in different behavior when you put in magnesium, sodium hydroxide, or check the conductivity. All right. Oh, here we now have the short answer questions. Define the term strong and weak acid and illustrate them. Well, basically, the definitions that you see, strong acids completely dissociate, weak acids only partially dissociate. But by that we mean, if I take a situation with HCl, for example, which is strong acid, that means it will react with water to form the hydronium ion plus Cl minus. It doesn't mean that HCl in aqueous solution falls apart itself to form H plus and Cl minus. Here, in fact, this is a classic Lowry-Bronsted reaction, acid reacting with the base to form the conjugate acid and the conjugate base. This is a conjugate pair. This is a conjugate pair. Remember, conjugate pairs are related by proton transfer. And so therefore, this is a strong acid simply because it goes to completion. It completely dissociates. On the other hand, if I take ethanoic acid, which you'll see shortly in the organic section, ethanoic acid is CH3COOH. It reacts with water in a similar manner, but it doesn't go to completion. Namely, it forms H3O plus CH3 COO minus. And it sets up an equilibrium And interesting enough, I happen to remember the K for this because I did many buffer calculations. The K for this is 1.85 times 10 to the minus 5 under ordinary conditions. So you can see that with the weaker acid, there's nowhere near complete dissociation. It only partially dissociates. All right, so this therefore is complete dissociation. And for this guy, it's partial dissociation. And that's how we can differentiate strong and weak. And as we saw on the multiple choice one, they will exhibit different behavior towards bases, magnesium, and in terms of conductivity. All right. Okay. Calcium carbonate is added to separate solutions of HCl and ethanoic. State one similarity and one difference in the observations you could make. Well, the similarity, since they're both acids, they will both react with calcium carbonate to evolve CO2. We've seen that equation before. So both will do that. So that's the similarity. The difference, however, is in this particular case that the reaction is more. Let me, oh shoot, let me change this. Erase this here. Go back to blue pen. It's a more vigorous reaction. With HCl. Ah, Peter. There we are. And we've seen the reaction before, but I'm asking you to write it again because this is going to come up in the part II question. So in this case, it's 2HCl, aqueous, plus calcium carbonate as a solid, goes to form CaCl2 as aqueous solution, plus H2O as a liquid, plus CO2 as a gas, which is evolved. And we saw that in the kinetics reaction. Now I'm asking you to write it again here because we need this, because every so often with acids and bases, this is where they sneak in a stoichiometry question. And you might think that since stoichiometry is topic number 1, it won't be dwelled on that much, but this is an easy way to sneak it in. And so you remember the 4 basic steps for doing a stoichiometric calculation. Number 1, you need the balanced equation. We have that. Number 2, you convert all given quantities into moles. You then do your calculation in terms of moles, and then you convert your final answer from moles to whatever is asked in the question. Always follow those 4 steps, and you're bound to get the stoichiometric calculations correct. So the first thing that you have to determine here is the number of moles of calcium carbonate, N of CaCO3. And that, of course, is simply dividing 1.25 grams by the molecular weight of calcium carbonate, which is 100.09. We'll say that's essentially 100, so this works out to be 0.0125. That's the number of moles that you have. Then the number of moles of HCl is then going to be equal to from the balanced equation, you know the 2 HCl react with 1 CaCO3. So the number of moles of HCl will be 2 times the number of moles of calcium carbonate, or 2 times 0.0125, which, if memory serves, if I can do this in my head, will be 0. Oh, Peter messed it up again. Erase, erase. Okay, let's go back to writing it again. And now my mouse is frozen. Why is my mouse frozen? What did I just do? Okay, I've hit a technical glitch here.
I
My
think
mouse is not responding.
if you press Control Z, and I think there is a interference
Control
between
Z.
you. Control Z.
Control Z.
Okay, that's it now.
The document.
Now there is, because there is an interference between your pen and your mouse.
Thank you. Highly technical here.
Thank
Keep
you.
the pen out of the way. Okay, thank you. That's why we need the boss here. He knows all these fine technical details. So this, therefore, twice that will be 0.0250. Number of moles of HCl. So therefore, the volume that you need of HCl will be equal to, you remember, N is equal to C over V, where N is the number of moles, C is the concentration, V is the volume. So therefore, V, in this case, will be equal to C over N. And so this case will be V is equal to C over N, which is 0.0250. What have I done here? It's 1.50 molar. Oh, I'm guarding against getting my pen in place here, and I end up mucking up the equation. V, oh, it happened again. Go back. Thank you. I'm just going to move my mouse completely out of the way. And all it does is mess things up. V, what the heck? Oh, I see, because I'm sitting on erase. There. So therefore, V is equal to C over N. There we are. So the concentration is 0.250 moles times 1 decameter cubed divided by 1.50 molar, 1.50 moles, right? Because my initial concentration is 1.50 moles per decameter cubed. And if I work out that number, the final answer turns out to be 16.7 centimeters cubed. All right, so the key point here is the stoichiometry. You can work out the number of moles of calcium carbonate because they give you the mass. Then you know from the stoichiometry of the equation that you need twice as many moles of HCl. And then you can convert that into the volume required because you know the concentration of the HCl. So this is then the concentration divided by the number of moles. And then they can always sneak in to calculate the volume of carbon dioxide measured at this. Now, again, you look at the balanced chemical equation and you notice that the CO2 is a 1-to-1 ratio with calcium carbonate. So therefore, the number of moles of CO2 will be exactly the same number as the number of moles of calcium carbonate that reacted, namely 0.0125. So by looking at the stoichiometry of the equation, you know that the number of moles of CO2 is equal to the number of moles of CaCO3, and that's equal to 0.0125. Now, you could then take PV is equal to nRT, because they give you the pressure. You can then do the conversion. You know the number of moles, you know R, you know temperature, so you could solve for the V. And then that's perfectly fine. But there's an interesting shortcut here, because these conditions of 273 K and 1.01 times 10 to the 5th pascals are exactly the conditions under which 1 mole of an ideal gas has a volume of 22.4 liters. (22.4 liters), or decameters cubed, as you guys have to write it. So therefore, in this particular case, all you then need to know is that therefore 0.0125 moles occupies 22.4 times 0.0125, and that works out to be 0.28 liters. 28 liters, or decameters cubed. So as I say, if you recognize this, because now you remember the new standard is 273 K and 1.00 times 10 to the 5th pascals, and the volume of an ideal gas then is 22.7 liters. But under these conditions is 22.4. Those were the conditions that I was raised on, so I recognize this. If on the other hand you don't recognize it, you can always plug in all the numbers and solve for V, because you know the pressure, you know the number of moles, you know the ideal gas constant, and you know the temperature. And you will get this final answer, 0.28 decameters cubed, or 280 mils. Okay, so as I say, it's not uncommon to see stoichiometry questions tucked in with acids and bases. You know, or you could have an acid-base titration type reaction in which you have to check, what is the combining ratio, 1-to-1, 1-to-2, and so on. So I would be on the lookout for that. Okay, that then takes us to topic number 9, redox processes. Oxidation and reduction. Oxidation states are assigned according to specific rules, and they're simply a means of keeping track of electron transfer. Oxidation is loss of electrons, reduction is a gain of electrons. The species that undergoes oxidation is the reducing agent. The species that undergoes reduction is the oxidizing agent. Okay, you have to keep those things straight. You then have to be able to express redox reactions using half reactions, either acidic or neutral solutions. There is the activity series of metals. We'll see that later on. You can have redox titration reactions, which again would be one of those in which you could have a stoichiometric type calculation, or you can carry out your redox reactions in electrochemical cells, which are the ones that undergo spontaneous transformations. So usually the electrodes are involved in the reaction, and you have to be able to represent the voltaic cell either in shorthand notation in a cell diagram, and we'll see one of those later on, or you have to be able to draw the cell complete with salt bridge and so on. And finally, there are electrolytic cells, which are the ones in which you impose a potential across a system to deliberately make it do the non-spontaneous transformation. That requires you to input energy to do that. The electrochemical cells run spontaneously and give you useful current that you can use to do things with. All right, let's see what sample problems we have here. Here we have a typical reaction, and we're trying to figure out who's the reducing agent and who's the oxidizing agent. And the answer chosen is A, because it's a reducing agent because it undergoes reduction. Unfortunately, that's not correct. If it's a reducing agent, that means it's giving away electrons. And if it's giving away electrons, it's undergoing oxidation. And so in fact, the first part of this is correct. H2SO3 is the reducing agent because you can see the tin goes from 4 plus to tin 2 plus. So clearly tin is the species that's being reduced. H2SO3 is the species being oxidized as it goes from H2SO3 to HSO4 minus. So it is the reducing agent, but it is that because it undergoes oxidation. Right? You have to keep that in mind because it sounds initially like a misnomer, but it's basically keeping track of where the electrons go. Okay. Oh, this is an electrolysis of a molten salt. So this is an electrolytic cell. Unfortunately, C is not the correct answer because in a molten salt, you don't have electrons. You have positive ions and negative ions. Think of something like sodium chloride. If you melt the sodium chloride, you have Na plus cations, Cl minus anions. They're the mobile species that are present in the overall melt. So there are no electrons. A gas is produced at the negative electrode? No, because if you think of sodium chloride, the Cl minus has to be oxidized to give you chlorine gas, which happens at the positive electrode, which is the anion. And positive ions will not move towards the positive electrode. They will move to the negative electrode. So the correct answer is both the positive and negative ions move toward their respective electrodes. Positive ions go to the negative electrode, which is the cathode. Negative ions go to the positive electrode, which is the anode. All right, and here we have a question that compares a voltaic cell and an electrolytic cell. Okay. The key point to remember here is oxidation always occurs at the anode. Reduction always occurs at the cathode. So it's C that's the correct answer. Because remember, there's a slightly funny notation that in your voltaic cell, they think of the anode as being the negative electrode and the cathode is the positive, and it's reversed for the electrolytic cell. But what happens at the electrodes, anode is always the site where oxidation occurs, cathode is always the site where reduction occurs. That does not change. And I think we have, no, here's the short answer now coming. All right, so here's a redox equation. And the first question is asked to determine the oxidation numbers of iron and manganese. Well, the iron is pretty simple because you're going from iron 2 plus 2 to plus 3. Right, because you're going from the Fe2 plus aqueous ion to the Fe3 plus ion. All right, manganese, on the other hand, in MnO4 minus, remember the rules are that each oxygen is -2. So therefore, the manganese here starts off as +7. And in Mn2 plus, it's +2. So Fe is going from +2 to +3. The manganese oxidation state is going from +7 to +2. So therefore, I'm looking down at the question II, you can see that this is the species that undergoes oxidation. And this is the species that undergoes reduction. And so the Fe2 plus is the entity that is oxidized. Or technically, I guess you would technically say here, the iron 2 ions are the species that undergo oxidation. In other words, they are the reducing agent. Now, I put this on because this is going to come up in the organic chemistry, and I get this question asked a lot. How do we get to these particular oxidation states? Well, let's take a look at CH3OH. CH3OH is methanol, and the oxidation state for that would be each hydrogen is +1. The oxygen is -2. So therefore, the carbon oxidation state in methanol is formally -2 oxidation state. Remember, oxidation states are assigned according to rules. CH2O, the oxygen again is -2. The hydrogen is +1. So in this case, carbon is 0 oxidation state. And the reason that I mention this is one of the reactions that you have to know in organic chemistry is the conversion of primary alcohols into aldehydes. And that's an oxidation described because they chuck in various oxidizing agents. And it's described as an oxidation simply because of this change in oxidation numbers. -2 in the alcohol, 0 in the aldehyde. Okay. Oh, yes. The reactivity series. You have to remind yourself, what is the activity series? This appears in the textbook, and here's a partial list. Magnesium, zinc, iron, lead, copper, and silver. So the first question says, all right, if you put a piece of copper metal in separate solutions of silver nitrate and zinc nitrate, which solution would undergo reaction? I'll let you think about that for a moment. Remember, the activity series indicates that the reactivity diminishes as you go down. And the classic mode of reaction of a metal is to give up electrons to function as a reducing agent. So in this particular case, if we have copper and we put that in a solution of silver nitrate and zinc nitrate, zinc is above copper in the reactivity series, so nothing will happen there. But something will happen with the silver because silver is lower in the activity series than the copper. So it's the silver nitrate solution that will undergo a reaction. All right, what type of chemical change is occurring in this particular reaction? This is true of all the metals as you go down the line, but in the case of copper, the reaction is that of an oxidation. The half reaction of which is copper goes to copper 2 plus 2 electrons. This is a subtle one that they sneak in periodically. What visible change would take place in the solutions? So you have to think about this insofar as if copper is undergoing oxidation, that means silver is undergoing reduction. Silver nitrate is AgNO3. Or silver plus. So if it undergoes reduction, it will form silver metal. If the copper undergoes oxidation, it's forming a copper 2 plus cation. So if we have simultaneously copper oxidation and silver reduction, the net equation that's going on, and I think this is useful when they ask you this sort of question to say, well, what the heck is going on here? You have copper reacting with 2 AgNO3, because you have to write it so that the electron transfer cancels out to form copper nitrate. Plus silver metal. That's the overall reaction that's occurring. So the thing that you then have to notice, the visible change that would occur is that this species is being precipitated out of solution. So you would get a dark precipitate forming. And they expect you to remember that copper 2 species are blue in aqueous solution. And so the answer, again, this is often an old exam question. The answer that they expect you to say is the solution turns blue, gray, or black as silver solid forms, and the copper ions form copper 2 plus, which are blue in color. And so the overall change would be a blue color with a dark precipitate forming, or a blue-gray mix. If you then wanted to utilize this reaction in a voltaic cell, the way that you would then indicate that particular cell, the shorthand notation would be to write copper solid boundary, copper 2 plus, and that's aqueous solution. Then you'd have the salt bridge. Then you'd have the silver plus aqueous solution. Boundary, silver solid. And so in the cell, you would then have copper and silver electrodes. You would have copper 2 plus and silver plus solutions. Probably the simplest thing is to have these both as NO3 minus solutions. And in your salt bridge, if you want ions that are about the same size, you could then put potassium nitrate. Because remember, without a salt bridge, the cell does not operate, because the ions have to move to compensate for either production of cations or reduction or reducing the concentration of ions. Or as I say, they could also ask you to draw the picture. You know, the two beakers, the salt bridge, electrodes, the wires, and they could ask you which way are electrons being transferred. You know what I'm talking about? I'll just do a quickie sketch here. Salt bridge, electrode here, another electrode here, through a voltmeter here. So if this is your copper here and your silver here, that's the conventional way of drawing it. The anode on the left, the cathode on the right, and the electron flow will be left to right. Okay, and these are in solutions of silver nitrate, of copper nitrate and silver nitrate. Okay. And that brings us to topic 10, which is a big one. Organic. Hey, Malula. I can't even fit it all on the screen. Barely make it. So clearly we can't touch upon all of these things. They often ask for the definition of homologous series, the different ways of representing the chemical formulae of organic compounds, nomenclature you have to know. You have to know the different functional groups. That's simply, you have to memorize them. Primary, secondary, and tertiary compounds, remember that's determined by how many carbon atoms are attached to the carbon that's carrying the functional group. If there's only one carbon attached to it, it's primary. If there are two, that's secondary. 3 is tertiary. The functional group chemistry, they tell you about the combustion of alkanes, the halogenation of alkanes, that's your classic free radical substitution. You have to know the mechanism of that, in which you need light to first cleave the halogen. That then generates a halogen radical. Then there are 2 propagation steps, which keep going round and around and around. And then there are 3 termination steps where the radicals combine. The addition reactions of alkenes, you can have bromine or the halogens, hydrogen or hydrogen halides. You can polymerize alkenes, or you can oxidize alcohols, and the products that you get will be dependent upon whether you have a primary, a secondary, or a tertiary alcohol. And we'll see that. Or you can have nucleophilic and electrophilic substitution reactions. So in the limited time we have available today, I won't be able to touch on all of these, but I'll touch on the most important aspects. But that mechanism of halogens reacting with alkanes, that comes up fairly frequently, this free radical substitution and the mechanism of addition of halogens to alkenes. These 2 particularly, I recommend that you know the mechanisms. That's outlined fully in the textbook. Whoops, mechanism. If I could write, I'd be in great shape. Oh dear, I did it again. Okay, back to pen. Okay, I'm not going to try to erase it. This is mechanisms. And you have to know those. There's just no way around it. Okay. So let's start off with a few multiple choice questions. Let's do the first one. Which compound is not in the same homologous series as the others? Oh my goodness. Remember, the homologous series is characterized by the fact that they can be represented by a general formula, and they differ by CH2 units. Clearly, the formula for these guys is CnH2n plus 2, which is true of all except B. Remember, there's your alkanes, alkenes, and alkynes, all of which have general formulae for their homologous series. All right. What type of reaction occurs when C6H13Br becomes the corresponding alcohol? Unfortunately, it is not D, because you're not adding anything. You're in fact substituting. You're substituting the Br with an OH. And formally, you're substituting, this is a Br minus, and you're substituting it with an OH minus. And Br minus and OH minus are both nucleophiles looking for positive species, so you're effecting a nucleophilic substitution. If it were an addition reaction, these two would combine together, but they don't. All right. Which compound can be both esterified and turn acidified dichromate green? Okay. To be esterified means it undergoes reactions to form esters. And the ester reaction involves a carboxylic acid combining with an alcohol, which I'll just represent this way. So R and R prime are just different organic groups. And the net reaction is that they combine to split out water to form R, C double bond O, OR primed, plus H2O. So therefore, in order to be esterified, it has to be an alcohol. So we look at these, that immediately rules out D. But it could be A, B, or C. So then the second requirement is it turns acidified potassium dichromate solution green. That tells you that it is capable of being oxidized by potassium dichromate. And potassium dichromate will only effect oxidation of, oh, sorry, I misspoke. We've ruled out D because it's not an alcohol, and we've ruled out B because it's a carboxylic acid. But I guess you could always argue the carboxylic acid could be combined with an alcohol, but it certainly will not turn acidified potassium dichromate green. In order to be oxidized, the alcohol has to be either a primary alcohol or a secondary alcohol. In this particular case, this is a secondary alcohol because it has two carbons attached to the carbon that has the OH group. This one here is a tertiary alcohol, which simply will not react with potassium dichromate. So to satisfy the first requirement, we ruled out D. We were skeptical about B, but the only one that satisfies the second requirement is C. The secondary alcohol will indeed undergo oxidation with potassium dichromate. And the last multiple choice one that you'll see today is this one. It is A. Good work, team. And again, they tend to ask this in a descriptive answer because basically these are all different forms of elemental carbon. And every so often they ask you to describe what are the differences between them. So that's something you should know. The typical short answer type questions. How is graphite different from diamond from C60? C60 is buckyball. Diamond is the extended covalent solid. Graphite has the sheet structure. And so that permits it to slide. Okay. So then, these are the commonly asked reactions that they ask on these tests. Because it wouldn't be an organic chemistry question if they didn't ask you to do reactions. So if I represent the C3CH28 group as R, in the first instance, I'm dealing with an R. Well, maybe I shouldn't do it that way. Let me put a carbon in here. RC, and I'll put a hydrogen here and a hydrogen here. So I'm abbreviating the long chain just to focus on the functional group. All right, potassium dichromate, as we've seen, is an oxidizing agent. Under acidic conditions, if you do the oxidation of a primary alcohol, which is what this is, the first product formed will be that of an aldehyde. So you will form RC double bond OH. So A will be the aldehyde. And if you're doing this preparatively, you have to essentially distill off the product before it can be oxidized further. And I have a nice descriptor of that. Some of you may have done the lab as well, because aldehydes can be oxidized further to finally form a carboxylic acid. That's B. So A is the aldehyde, B is the carboxylic acid. And that will not react any further. That's why in the multiple choice one, we knew it couldn't be the carboxylic acid because that wouldn't react with potassium dichromate. All right, so A is an aldehyde, B is the carboxylic acid. C is now the nucleophilic substitution, in which, again, if I write that reactant as RCBr, that gets treated with sodium hydroxide, which is essentially is OH minus. That then gets converted to the corresponding alcohol. So I should put a couple of hydrogens on here. So C is the corresponding alcohol. Okay. Then we look at reaction number 3. Now, reaction number 3, you have to be careful. You have a carbon, a hydrogen, another carbon out here with a methyl group, another carbon down here with a methyl group, and the OH. So this is a secondary alcohol. And secondary alcohols are oxidized differently than primary. We saw with primary, you first get an aldehyde, then the carboxylic acid. In this particular case, using the same oxidizing agent under acidic conditions, you then end up forming the corresponding ketone. CH3, H. Well, let me just put it out here. C double bond O, right? So you end up forming a better picture to be this way. CH3, because we know from our Lewis dot structures in VSEPR that the environment around the central carbon in this particular ketone is trigonoplanar. And this is also called 2-propanone, or more commonly acetone. So this is D. D is the ketone. And the final one, E, where you're now reacting bromine with the carbon-carbon double bond. This is the one where I've said you really should know the mechanism. This is BR attacking this way. Slightly delta plus here, delta minus here. This then uses the one component of the double bond to form the link. That then cleaves this. So you transiently generate CCBR, C that carbocation that then has a Br minus that can then attack it to give you as the final product, each one carrying a bromine. But it's a two-step mechanism. Essentially, it's electrophilic attack to break one component of the double bond to form the link to the bromine. That cleaves the bromine-bromine bond and liberates the Br minus, which can then attack the carbon, which is the form of carbocation, to give you finally this product E. So E is the dihaloalkane. So this is known as dibromoethane. Okay, so those are the typical modes of reactivity that occur in chapter 10 in the textbook. Primary alcohols oxidized initially to aldehydes, then carboxylic acids. Nucleophilic substitution converts a haloalkane into the corresponding alcohol. A secondary alcohol gets oxidized to a ketone and Br2, and you can have the same sort of thing. Here you can also have H2 undergo addition or HBr. So if you have H2 addition to this, then of course you end up forming the alkane. If you had HBr, you would put an H on this one and a Br on this one, and you'd end up forming the monobromoethane, and so on. Okay, all right. So those, again, those occur very frequently on the final exams. So here they tell you that ethylene, ethene, I have to be careful using my common names here, can react to form a polymer. Name this type of polymer. The key point here is that this is essentially an addition polymer. In which the units simply add. You break the double bond and you simply link up the situation in which they keep adding. And so therefore, I guess you could put all this here sort of thing So this would be the repeating unit. And you can write it as N. And then you would just have CH2 groups going on ad infinitum. And the point about this polymerization, this is true even for substituted alkenes. So suppose you had CH, let's say Br here, then it would form a polymer where this would be the repeating unit, and so on, right? It simply results from the double bond being broken and forming a single bond to form a chain of species. And usually they ask you to draw a section if they want 3 repeating units. I've done that. But now you can then indicate the central unit and put an N to indicate that's the one that keeps repeating all along. Okay. All right. Oh, and here's a computer-generated representation of 2-hydroxybenzoate, methyl 2-hydroxybenzoate, better known as oil of wintergreen. And the first question they ask you is, what is the empirical formula of 2-hydroxybenzoate? And they want you to draw the full structural formula, including any multiple bonds. Because, of course, in the computer-generated representation, when you do the structure, you don't know whether these are single bonds or double bonds. So perhaps the easiest thing for us to do initially is to draw the structure and then take it from there. So if I put it here, I could go this way, like so. And then from here, I have an OH group. And then down here, I have a C double bond O, OCH3, right? And then I have hydrogens out here, hydrogens all the way around. And of course, I see this ring. I could draw double bonds, but I know I'm mindful of resonance. And so the simplest way to represent this is to simply to put the circle in there. So that you got the recognition that all the carbon-carbon bonds within the 6-membered ring, so this is essentially a derivative of benzene. So all the carbon-carbon bond lengths are intermediate between single and double bonds. And that ring is perfectly planar. So this would be the representation. So then I have to count my carbons and all this. And I come up with the empirical formula that it's C8, H8, O3. And I believe that's correct. C8, H8, 4, 5, yes. Again, they could then ask you, what bond angles do you expect? So for example, what bond angle would you expect here? This is sort of reminiscent of water. Remember you got, oh, don't do that to me. What have I done now? Close that. This is essentially like the situation in water. I've got 2 lone pairs of electrons around the oxygen. So this bond angle will be on the order of 104, 105 degrees. These will all be about 120. This again was comparable to what I had up here. And this now is a C double bond O, so I would expect this bond to be shorter. Than the CO bond here, because that I invoke a single bond. Remember, bonding theories are rationales after the fact. Okay, we invoke resonance for benzene simply because we know that in the structure of benzene, it's planar and all the carbon bond lengths are the same length. It's not because Lewis Dots said, oh yes, there must be resonance, hence the bonds will be equivalent. It's the other way around. So then, empirical formula. So then they say, two of the carbon-oxygen bond lengths are 1424 and 1373. Okay, so this is going to be the 1424, the longer one. This will be the 1424. What do they have them in? Picometers? Was that picometers? Yes, 14 nanometers. This will be 0.1424 nanometers. And this will be the shorter one. It was a 1373. Yes, 1373 will be this guy. 0.1373 nanometers. Okay. Then they say, so what would you predict the carbon-oxygen bond length and carbon dioxide to be? So that then requires you to play Lewis dots. And you know that each oxygen brings in 6 electrons, the carbon brings in 4. So you have 16 electrons in total to bring in. So there's 2, 4. So I need 6 more. So I could put 6 around each oxygen, but that leaves me short on the carbon. So the only way I can satisfy the octet rule is to put 2 lone pairs on each oxygen, like so, and like so, and like so, and invoke double bonds here. And so CO2 is a linear molecule. This takes you back to topic 4, and you'd expect the CO bond to be the shorter one, 0.1373 nanometers, and in fact it is. And this brings to mind the other trick question that comes up, and that is silicon dioxide. Your first impulse might be to say, oh, well, silicon just sits below carbon, sorry, and so it'll form a similar sort of nice SiO2 molecule. Unfortunately, that is not true. Carbon dioxide is a gas. Silicon dioxide is the sand on the beach. Simply because SiO2 is a covalent polymeric solid, extended macroscopic covalent solid. And every so often they ask you to contrast that, and that's simply because the silicon likes forming 4 single bonds to oxygen in this extended array. So this links to other silicons like so, all the way along, rather than form double bonds, as the carbon does. That's the fundamental difference between the two. One is a covalent network solid, one is a nice triatomic gas. All right, and finally, they want you to name all the functional groups present in wintergreen molecule. Well, you have a ketone, or you have an ester, if you want to think of it that way, or you can think of this as a ketone functionality. But I think it's probably best, this is an ester overall. This is an alcohol. And you also have the arene or benzene ring. That is a functional group because at the end of chapter 10, they show you that the arene ring, the benzene ring, can undergo electrophilic substitutions because it's electron rich, which contrasts with nucleophilic substitutions that you see with the haloalkanes. And that brings me to the end of the formal presentation. I notice we still have a few more minutes. Are there any questions that need to be elaborated upon?
Well, I think that
everything was very beautifully presented, clearly understood by
exactly.
everybody.
It seems so. It seems so. Well, at least we had a few questions during the class, but again, if you have any questions, you can ask. But if there is nothing, just I would say thank you for participating, and we hope it was useful. Like last time, you can give your feedback, send us an email. And last time, one of the students got the $50 gift card for their feedback, and we talked with Peter regarding that, and it was really great. So, but this is a 2-hour workshop. So in 2-hour workshop, I think this is the best that we can do, and hopefully we will have more next year's. Okay,
yeah, remember we focused on the highlights. There are other things that we didn't discuss specifically. I tried to bring them up as we were talking about them, especially these organic reaction mechanisms. That's a very favorite topic.
It is pretty straightforward, but a lot of students have problems over there. Well, I mean, it was very good for me because as a rustic chemistry teacher, it was pretty refreshing. And our idea was that at the beginning that you guys should have studied a little bit and come here. If you don't study and come here, it's going to be pretty confusing, definitely. So Peter was not going to explain everything from zero. That would have been like, I don't know, 20, 30 sessions at least. And unfortunately, we can't do it right now. Hopefully next year, who knows? Okay, thank you everybody for participating.
And good luck on the final exam.
Yeah, good luck with the final exam. Thank you everybody. Have a great day. Bye now. Bye.
Take care.